So this is going to be what I expect to be a really short lecture. That doesn't mean that this topic isn't important. It's a hugely important topic. It's just that the topic is so massive to do anything in one class that's going to do nothing but confuse you. And so I was told to cover this section lightly, and I'm taking that very literally and covering it very lightly. So section 8.7 is covering a topic called linear programming, and linear programming is a huge field. Basically, linear programming finds its way more into the business environment more so than in the sciencey environment. Linear programming is a mathematical strategy used to allocate resources. For instance, in World War II, there was a big shortage of raw materials, but there was the need to produce as many bombs and tanks and whatever they needed to produce as possible. And linear programming is the strategy that was used, the problems that can be solved under the topic of linear programming basically helps you allocate resources effectively to maximize your profit if you're a business, minimize costs possibly, or maximize your production if you're the government going to war. So it's a huge topic, so huge that Excel has the ability to solve linear programming problems, and so huge that we just can't do a good job in one little lecture. If you take Math 172 or Math 218, or if you're a business major and you take an operations research class, you'll most definitely spend probably the better part of a month studying linear programming, which means maybe you'll get 8 to 10 lectures on the topic. And those 8 to 10 lectures won't cover the topic as deeply as it can be covered, but you'll get a better understanding for why we study this field. And so it's hugely important, comes up a lot, but in 1 hour class, you can't really even do anything. You can't really even scratch the surface. So I wrote up 10 problems, 5 evens and 5 odds. I'm going to do the 5 evens, and the seeds for this particular problem set were kind of sown when I did section 8.6. The last problems that I did, the problems kind of between, I guess, 31 and 40, maybe 32 and 40, all had a system of inequalities that we graphed, shaded, and found corner points. That somehow was going to be the most important part, or the hardest part, of solving a linear programming problem. This particular problem 2 from section 8.7, I say maximize this function z subject to these constraints. In a real world problem, it might be maximize your profit subject to I only have this much raw materials and I only have these many workers, and if the workers work overtime they start getting paid more. So subject to these real world constraints, tell me how many of these autos, if I'm producing cars, to produce to potentially maximize my profit. So my goal is, subject to the constraints, find the largest value that this can be. So I'm trying to maximize z. This equation on Excel, they call this a target equation. In a lot of textbooks, they call it an objective function. But my goal is to find the largest value of z that meets with these constraints. And these subject to are called the constraints. Because if there were no constraints, I can plug in, in an infinity for x and infinity for y, and z can be infinity. But for this particular problem, the x's and y's are subject to some constraints, which binds how big z can get. So to solve a linear programming problem, the first step is to graph the constraint equations and find the corner points. There's a theorem called the fundamental theorem of linear programming, which says if your goal is to maximize or minimize a constraint function or an objective function or a target function subject to constraints, and all the functions are linear, there aren't any squares or cubes, that the maximum, if you're trying to get the maximum value or the minimum value, always occurs at a corner point. It might occur at other points than a corner point. You might get a tie somewheres, but you'll never produce a higher value if you're trying to maximize or a lower value than if you're trying to minimize. So the algebra for solving a linear programming problem is to first graph the constraints, find the corner points. And that's already been done because when I did my lecture for problem 32, section 8.6, this is the graph that I came up with. I saved my notes when I did the video from section 8.6. I just copied this in. So if you took notes when you were watching section 8.6 and as I was doing problem 32, this is what you would have copied in. So I just did that, so I didn't want to do the graphing again. To find the optimal, the biggest z can be subject to these constraints, it's easy. So once you have the graph generated, shaded, and you find the corner points, then the maximum value of z occurs at one of the corner points, and then all we need to do is evaluate the maximize function at each corner point. Realize this is not a stellar lecture. To do a stellar lecture, it would take gobs of time. I taught Math 172 for years because I used to be an accountant before I taught here, and probably from 1994 to 2001, I taught a few sections of Math 172 finite math every semester, and we did a month of this, maybe 5 weeks of this every semester. So I have a lot to say about the topic, but just don't think I can do it properly, so I'm doing a really, really condensed lecture here. So to solve any linear programming problem at the college algebra level, you graph the constraints, you shade, you find corner points, then you take each of the corner points and put them into the function that you're trying to either maximize or minimize, plug the x value and the y value in, and simplify. When I plug 0, 0 in, I get 0 plus 0, which is 0. When I plug 0 in for x and 5 for y into the maximize function, I get 0 plus 12 times 5. And that's 0 plus 60, which is going to be 60. When I take the 2, 3 and plug it in, I get z is, I put 2 in for x, 3 in for y. I get 2 plus 36, which is going to be 38. And then the last corner point is the point 3, 0. When I plug into the maximize function 3 for x and 0 for y, I get 3 plus 0, which is 3. My goal is to find the biggest value that z can be subject to these constraints, and there may be some other point in this constraint region that produces a value of 60, but no one that produces a value bigger than 60. And then outside the final shaded region, there are definitely values of points that produce numbers bigger than 60, but those points would violate one of the constraints, so they're not acceptable. So my answer to this problem is the maximum value that z can take subject to these constraints. I'll say the maximum value of z is 60, and it occurs at the point 0.05. So I can know nothing about linear programming, and I can solve these problems reasonably effectively, and that's basically what I'm going to have you do, more so than give you a real understanding, like I said, because a real understanding is going to take way more time than we have, and if you're a business major, you'll definitely see linear programming again. So that's all there was to do for every single problem in this section. Take the constraint equations, graph them, find the corner points, take the corner points, plug them into the equation that you're trying to maximize or minimize, and pick off your solution. Problem 4 also has its seeds from section 8.6. My goal is to find the biggest value that z can take for this equation, subject to these constraints. So, x likely can't be 1,000,000 because it's going to somehow violate the constraints. So step 1 was to take these constraint equations, graph them, and find the corner points, and that's exactly what I did when I solved problem 34 in section 8.6. I just took the sheet of paper that I wrote the answer to problem 34 section 8.6 when I did that video and copied it here. Now I'm going to take each of the corner points that came from my answer, from my shading, and plug them into the target equation, or the maximized equation. We say target equation, objective function, the maximized equation, so maybe I'll just say value. So I'm going to take the point 0, 0, and plug it into the z function. I'll go z equals 9 times 0 plus 20 times 0. When you do that, you get 0. I'll do the same thing for 0, 6. Get z equals 9 times 0 plus 2 times 6. When you do that, you get 0 plus 12, which is 12. And then the 7/3 0 is not so pleasant. 7/3, and I skipped the 1, 4. I'll get back to it. When I do the 7/3 0, I go 9 times 7/3 plus 2 times 0. The 2 times 0 is not hard for me. The 9 times 7/3 really is 21, but I'll do it on my calculator just in case you didn't know how to do that. If I went 9 parentheses 7 divided by 3, that will multiply 9 times 7/3, and it comes out to be 21. So if you didn't want to do the fraction math in your head, then you could do that on your calculator. In fact, you can do all this arithmetic on your calculator. It's not anything that your calculator couldn't handle just fine. The last one, I put 9 times 1 is 9, plus 2 times 4 is 8. 9 and 8 is 17. Because I'm trying to find the maximum value for z, that's going to be, subject to these constraints, its maximum value is going to be 21, and it occurs at the point 7/3 0. So for my answer to this problem, I'll say the maximum value that z can have, subject to these constraints, is 21, and it occurs at the point 7/3, 0. The next 3 problems are essentially the same, except the word next to the z says minimize. And when I go to find the best point, I'm going to be searching for the point that gives the smallest value. This is like in a business, if you're trying to minimize your cost, then you're looking for the smallest value as opposed to the largest value. This might be like in a business, I'm trying to maximize my profits or maximize my production. In that case, I was looking for the biggest as opposed to the smallest. But in the next 3 problems, I think, the word next to the z function, which I might call the objective function or the target function or target equation, objective equation, says minimize, and I'm going to find the smallest value of a corner point that will generate my solution. So same deal here. The constraint equations were the same as problem 36, section 8.6. On a few of the problems in section 8.6, you didn't have the or equal tos, and I changed some greater thans to greater than or equal tos and some less thans to less than or equal tos, because in linear programming, the endpoints have to be part of the solution, potential solution. So that there's a subtle difference where on my graph I might have a dashed line as opposed to the solid lines that I have here. Nevertheless, the solution for any linear programming problem, once you've graphed the constraints, shaded, found the corner points, you're going to take each of the corner points and plug them into the function that you're trying to maximize or minimize. In this case, I'm trying to find the smallest value of z because it says I'm minimizing. I'm going to plug in each corner point. For the first corner point, 0, 9, I get 0 plus 360 if I do that arithmetic, which gives me 360. The second corner point, I plug 2 and 3 in for x and y. I get 10 times 2 plus 40 times 3. When I do that, that's 20 plus 120, which is 140. And when I plug 5 and 0 in, I get z equals 10 times 5 plus 40 times 0. That comes out to 50. And because my goal is to find the smallest value of z subject to these constraints, the smallest value z can be, or the minimum value z can take, is 50, and it occurs at the 0.50. So the answer under subject to these constraints, the minimum value of z is 50, and it occurs at the 0.50. The next two problems, 8 and 10, are exactly the same style of problem. In fact, all the problems in this section look the same. The only subtle difference is the word minimize as opposed to maximize, and that makes me look for the smallest number as opposed to the biggest number. For each of the problems, just to speed up the video, I made the problem, the constraints come from a problem in section 8.6, copied the picture. You can do this picture by hand, but I generated this picture when I did the lecture of section 8.6. So problem 8, the constraints come from problem 38, section 8.6. This is the graph that I had when I did those particular, I did that problem. My goal, subject to these constraints, is to find the minimum value for z. This is actually a bad problem, but I didn't take it out. I'll live with it. If this was like a word problem, it would be kind of funky in terms of the answer isn't probably something that I would have wanted. But for this, it's completely fine. So I have 3 corner points, 5/3, 0, 0, 0, and 3, 2. My goal is to separately plug each one of those x's and y's into the minimize equation and see which one gives me the smallest value. I know it's the middle one. I could do that one in my head. For the top one, the 50 times 5/3 was not a good thing for me to do right now. So I did 50 times 5/3, and I get 83.3. It doesn't matter how much I do or don't round, because this isn't going to be a solution point, so it's irrelevant if I round or not. For the middle one, I get 50 times 0, which is 0, plus 15 times 0, which is 0, and that's 0. And the bottom one, I get 50 times 3 is 150, plus 15 times 2 is 30. Add those, and I get 180. My goal is to find the minimum value z can take subject to these constraints, and that must be 0. So I'm going to say for my answer, the minimum value of z is 0, and it occurs at the point 0, 0. Surprisingly didn't go off the screen. And one more to do, and they're all exactly the same. Had I not produced the graphs or copied the graphs from the last section, it would have taken way longer to do this. But if I ever test you on this, it'll probably be right after I have you do a graph from a problem similar to 8.6, and then I'll just extend the question. So last one, as another minimize. Again, the constraint equations are the same, or constraint inequalities are the same as a problem from section 8.6. These inequalities were the same as problem 40 from section 8.6, so I just copied that graph down to speed up the process. We can definitely find the x and y intercepts, find where the lines intersect, figure out how to shade, and then get into the linear programming part. for the linear programming part, once you have the graph and you know the corner points, you take each of the corner points and put them into the minimize equation. For the 0.09, I get 0 plus 63, which is 63. For the 0.23, when I plug it into the minimize equation, I get 6 plus 21, which is 27. Because my goal is to find the minimum value that z can take subject to the constraints, the answer is going to be 27. So the minimum value of z, it's almost right, value of z is 27, and it occurs at the 0.23. There's a ton of videos on linear programming on YouTube, and I tried to find one that would just explain better why we're studying linear programming, but every video that I saw was essentially awful. One was maybe more awful than the next, so this kind of is what it is. So algebraically, it's not that challenging of a section. If you're able to graph a system of inequalities, shade and find the corner points, then to minimize or maximize a function is just one more step, taking the corner points, plugging them into the equation that you're trying to maximize or minimize, and finding the biggest or smallest number depending on if you're looking for the biggest or smallest number. All right, that has to be a record for the semester. I don't think that even took a half hour. And that's all. I'd never ask more than that. So everything that you're responsible for in terms of linear programming.